Okay, so here's our picture. Here was our state psi. This was the test run. And then for each step, our state moves by at most 1 over square root n. Okay, but now how much can it move as a result of t such steps? At most t over square root of n. Okay, but now when you make a measurement, how much effect can this have on the actual probability of seeing something? So the probability changes by the square of this, order the square of this, which is order t squared over n. And that's the maximum it can change. So the worst that can happen to us is that all these little changes in each step line up to get constructive interference. And when you get constructive interference, you get this t squared term show up. And that's because it's constructive. And so what Grover's algorithm manages to do is it manages to make these terms line up. So if you want to understand it, go back and look at Grover's algorithm, and you'll see in what sense these changes line up, and you get constructive interference. And so you get exactly this effect. So this effect showed that you could do no better, and Grover managed to find a method of actually matching this lower bound. Okay, so now let's try to understand what we just saw before, where we said that no quantum algorithm can solve this search problem with better than quadratic speedup. We also saw in the last lecture that how this search problem corresponds to solving an NP-complete problem, because the entries of the table, well, they could correspond to different possible assignments to the truth values of a satisfiability formula, and those are the indices of the entries, and the entries themselves just say whether it's a satisfying assignment or not a satisfying assignment. And so if you're looking for a satisfying assignment, and we think of it as a marked entry, then the search problem corresponds to solving satisfiability, or an NP-complete problem. So have we shown that quantum computers cannot solve NP-complete problems in polynomial time? Well, the answer is no. We haven't shown that, because what we've shown is that if we can think of our problem as a black box problem, so if we are saying that we don't understand anything about the structure of the satisfiability problem, so we can't just look at the formula and syntactically based on what the formula looks like, maybe there's a fast algorithm that decides whether it's satisfiable or not. So what this is ruling out is that there's no way to actually evaluate the formula in superposition without understanding what the formula means and solving it quickly. In other words, to do any better, you have to understand the structure of the problem. What makes this so difficult is that people have been trying to understand the structure of NP-complete problems for several decades, and we don't know how that works. We haven't found much non-trivial structure to work with. About 10 years ago, there was a beautiful paper by Eddie Fari and his collaborators at MIT, where they proposed an algorithm for solving satisfiability. This is the so-called adiabatic quantum optimization framework. And they were unable to analyze this algorithm, but they ran simulations on small instances, of size n equal to 10 or 15. And what they found very exciting is that these simulations were consistent with polynomial time solution. So here's a pointer to that paper. You know, you should it's worth chasing up and reading. Okay, and then a few years later, there was a company that was launched. It was called D-Wave Systems. It's in Canada, in Vancouver. You know, it implemented this algorithm. In fact, you know, the company's launching its demonstrations were met with a lot of enthusiasm from the media, including The Economist, which in an unrestrained way talked about how the first practical quantum computer had been unveiled. It talked about how you know, British Columbia was going to become the new Silicon Valley, and well, there was a, you know, the Economist article was of course extremely over enthusiastic. So let me, you know, I'll try to put it in perspective. But it was talking about how quantum computers provide this neat shortcut to solving NP-complete problems by putting qubits in a superposition of 0 and 1. But then they made this mistake. Remember how in the last lecture we talked about how you can't just put your qubits in superposition, compute the function, and hope to find the marked element, because by the rules of measurement, you won't see, the chance you'll see the marked element is exactly the chance you would see it if you ran a probabilistic algorithm. Okay, so the Economist fell into this trap of making this mistake. But okay, so let me say a little bit in 2 minutes about what adiabatic quantum computing is. So what you do is you design some Hamiltonian H, which is easy to implement, and such that the ground state of this Hamiltonian H sub final is the output. It's the output to the problem that you're trying to solve. But this is of course a solution which is hard to find. So you don't know how to find this solution. But you also design an easy Hamiltonian whose ground state you already know. And now what you do is you start in this ground state of the known Hamiltonian, the initial Hamiltonian, and you gradually transform the Hamiltonian from H0 to HF by taking a linear convex combination of the two. What the adiabatic theorem says is that if you do this slowly enough, then you'll drag the ground state from this known ground state psi naught to this target ground state psi sub f. So if you do this slowly enough. But how slowly? Well, how fast you can go is 1 over the square of the gap between the ground energy and the first excited energy. So if E naught equal to the ground energy and E1 is the first excited state's energy, then the gap is E1 minus E naught. And so how fast you can go depends upon the smallest gap during this transformation. Okay, so here's an example that shows you how to encode 3-sat as a local Hamiltonian problem, how to write out the Hamiltonian H sub f so that its ground state is a solution to this satisfiability problem. In fact, what we are going to write is we are going to write H sub f as H1 plus H2 plus H sub m. So there's going to be a term of the Hamiltonian for each clause here. Sorry, this is going to be a little fast for most of you, but I'm just giving you sort of a perspective for those who can follow this. Okay, so the n bits get transformed to n qubits. The clause x1 or x2 or x3 corresponds to an 8 by 8 Hamiltonian matrix which is acting on the first 3 qubits. It assigns a penalty of 1 if the clause is not satisfied. So the only way to not satisfy the clause is if x1 equal to x2 equal to x3 equal to 0. So you put a 1 in this lower left corner, and then zeros everywhere else. So it's going to be a diagonal matrix with a penalty of 1 corresponding to this truth assignment, where the only assignment that does not satisfy this clause. And now what you can check is that the satisfying assignment for this formula corresponds to an eigenvector of this Hamiltonian with eigenvalue 0, and all other truth assignments are eigenvectors with eigenvalue equal to the number of unsatisfied clauses. So the ground energy is exactly, the ground state is exactly a satisfying assignment to the formula. Okay, remember how fast we can go depends upon the minimum gap. It turns out that there are a few things that are known about this problem. So it's known that the adiabatic optimization can be used in a certain way to give you quadratic speedup for search, but that in general it takes exponential time. It can also be it's also been shown that in general it takes exponential time for NP-complete problems, but that if you set up the problem in certain contrived ways, then you can tunnel through local optima. And then there's this paper that shows that using arguments, using arguments from Anderson localization, it shows that the algorithm typically gets stuck in local optima. So what does all this say about this endeavor to build quantum optimization, adiabatic optimization, and the D-wave computer? Well, the consensus of the research community right now is that it's unlikely that this algorithm will work well for any interesting problems, that it will give us a speed up for interesting problems. However, there are reasons that D-wave is trying to implement this, and the reasons have to do with the fact that it's actually easier to implement than general quantum computing. And so it's a long shot. It's a very long shot. But somebody should be doing it. So it's very unlikely to succeed, but on the other hand, maybe, given that it's so hard to analyze adiabatic quantum optimization in general, even though the indications are that it's not going to give a speed up for typical problems, it's worth trying to implement it and check whether on the off chance it actually gives a speed up for certain kinds of problems.